Hi everybody. In this video, we're going to talk about evaluating limits with trig functions. So we're really still evaluating limits analytically, meaning using algebra, but we're just given trig functions, okay? Now, before we get into limits, this is a good time for you to review your unit circle because you're going to need to know your unit circle in order to evaluate trig functions. And in some cases, we will use trig identities to maybe rewrite or simplify the function. These are not the only trig identities, but ones that we tend to use through calculus. Mainly the reciprocal quotient and Pythagorean identities, I would say, are the most important for you to know. All right, so let's get into some limits. So remember, to find limits algebraically, we said you would always try direct substitution first, and that does not change. Even with trig functions, always try direct substitution first. So here's an example. The limit as x approaches 0 of 1 plus cosine x divided by 3 plus x. If I try direct substitution, this will become 1 plus cosine of 0 divided by 3 plus 0. To find cosine of 0, that's when you're going to go to your unit circle. And remember, cosine of the angle is the x-coordinate, so this angle is 0 radians, and so cosine of 0 equals 1. So then, going back, this will just become 1 plus 1 over 3 plus 0. And so we just end up getting 2/3. And that is the answer to the limit. Okay, so even with your trig functions, try direct substitution first, because a lot of times they'll throw one in there and you'll try to manipulate it and rewrite it, and you never needed to do that. You just had to plug it in. Okay, now, what happens if you try direct substitution and you get an indeterminate form, like 0 over 0? Well, one thing you can do is try rewriting the function using your trig identities. And in this case, we've got the limit as x approaches 0 of 1 minus cosine x divided by 4 times sine squared of x. So anytime I see that sine squared of x, that gets me thinking about my Pythagorean identity. So let me go back to our identities. This is the main Pythagorean identity, sine squared of the angle plus cosine squared of the angle equals 1. But remember, we can break that down into 2 additional identities. So we could actually use this one and replace sine squared with 1 minus cosine squared. All right, so let's go back. So this will become the limit as x approaches 0 of 1 minus cosine of x over 4, now times 1 minus cosine squared of x. And again, that's just replacing sine squared of x with 1 minus cosine squared of x. Okay, now you might be thinking, wait, but that didn't do a whole lot. Well, you can also factor these, okay? So 1 minus cosine squared of x is difference of squares. So we can actually factor that. So now we have the limit as x approaches 0 of 1 minus cosine x over 4. And now I'm going to factor the 1 minus cosine squared x into 1 minus cosine x times 1 plus cosine x. Now that's helpful because we can now simplify. And so this will now become the limit as x approaches 0 of 1 over 4 times 1 plus cosine x. All right, well, let's just see if that helped us. Let's try direct substitution. 1 over 4 times 1 plus cosine of 0. And remember, cosine of 0 is 1. So this will become 1 over 4 times 1 plus 1. Or 1 over 4 times 2, or 1/8. All right. So again, we just had to use our trig identities, replace sine squared with 1 minus cosine squared, and then we were able to factor and simplify and then try direct substitution. All right, now for some of these limits, we will use these two important limits. And I will tell you that they are proven using something called the squeeze theorem, but I don't want us to get too bogged down into the squeeze theorem because it's not actually on the AP exam. But these are just two limits that right now you want to put into memory. The first one is the limit as x approaches 0 of sine of x over x. We know that is always equal to 1. And then the second one is the limit as x approaches 0 of 1 minus cosine x divided by x equals 0. Now, let me talk a little bit about these because you can actually manipulate these even. This first limit will work if it's the reciprocal. So the limit as x approaches 0 of x over sine of x also equals 1. Okay? And it will also work if, let's say, it's the limit as x approaches 0 of sine of 2x over 2x. So as long as these numbers are the same, then you can use this identity. This would also equal 1. Okay, so let's get to some examples down here. In our first example, we have the limit as x approaches 0 of sine of 4x divided by x. So here's the thing. We can use this limit, but we need, because the numerator is sine of 4x, we need the denominator to be a 4x. Okay? Then that limit would equal 1. But if I multiply the denominator by 4, I also have to multiply the numerator by 4. That way I'm just multiplying by 4 over 4, which is 1. It's not going to change anything. We're just kind of manipulating it. Okay, so now what I can do, this is also where some of your limit laws or properties of limits come in. This 4 is a constant multiple, so I can actually move that in front of the limit. Now it'll look like this, and then we know that this limit is equal to 1, okay, based on our special limit. So this will just become 4 times 1, which equals 4. Okay? Okay, same idea with example B. We have the limit as x approaches 0 of sine of x divided by 3x. So again, in order to be able to use the property, we need, well, actually I take that back. We could just use our limit law here and think of our constant multiple as 1/3. So we could move a 1/3 out front and make it 1/3 times the limit as x approaches 0 of sine of x over x. And now we can use that property or that special limit, and this will become 1/3 times 1, which equals 1/3. It's all about kind of manipulating it to be able to use that special limit, okay? But you're going to see a pattern here in a minute, and you'll find that these are actually pretty easy in the long run. Okay, now we have here, so in example C, we're going to kind of combine what we did in both A and B. We've got a constant multiple, so 1/6 we could move out in front using our limit laws. So now we have 1/6 times the limit as x approaches 0 of sine of 5x only over x. But again, in order to use the special limit, we would need a 5x in the denominator to match the 5x in the numerator. But again, the idea is if I multiply the denominator by 5, I have to multiply the numerator by 5. But I can actually do that on the outside because it's a constant multiple. So now I have 5/6 times the limit as x approaches 0 of sine of 5x over 5x, which I know this is equal to 1 using our our special limit. So this will become 5, 6 times 1, or 5, 6. Okay, so I hope you're kind of seeing a pattern here. Whenever you are faced with finding the limit as x approaches 0 of sine of a times x over b times x, this is simply just going to equal a over b. If you go back to our original problems, in this case, the a is 4 and the b is 1. And so we got 4 over 1, or 4. Okay, in this next example, your a is 1 and your b is 3. And remember, we got 1/3. And then in this example, a is 5, b is 6. And remember, we got 5, 6. So these can actually be pretty easy if you remember that pattern. All right, let's look at a few more examples. If you look at example D, anytime you're given tangent, you pretty much have to use your trig identities to rewrite it in terms of sine and cosine. So I'm going to use the quotient identity and replace tangent with sine over cosine. And so it's going to look a little ugly at first because we're going to have sine over cosine all over x. But then, because we're dividing fractions, I'm going to multiply by the reciprocal. So I'm going to make this sine of x over cosine of x times 1 over x. Okay, now I'm going to manipulate this a little bit and just kind of mix up our terms because I want to use my special limit, sine of x over x. So I want this x, like I'm just going to switch x and cosine of x. And I can do that because we're multiplying and order doesn't matter when you multiply. So I'm going to rewrite this as sine of x over x times 1 over cosine of x. Okay, then I can use one of our limit properties that says if I'm finding the limit of a product, I can break this up into the product of the limits. Okay, and then this is our special limit, so we know that equals 1. And then for this limit, I can just do direct substitution. This will become 1 over cosine of 0. But remember, cosine of 0 is 1, so in the end, this all equals 1. All right, let's look at E for a minute. Okay, so here we have, I'm seeing this 1 minus cosine squared of x, which is getting me thinking about my Pythagorean identity. So let's just try it. Let's replace 1 minus cosine squared of x with sine squared of x over 3x. And then let's just kind of break this apart using multiplication. Because remember, sine squared of x means sine of x times sine of x. And because I want an x under my sine of x, so I can use that special limit, I'm going to do that. And I think I'm just going to put the 1/3 out front as a constant multiple. This would be like a 1 in front. Okay, so now I have 1/3. And remember, I can use my limit laws to break apart my limits. I'm going to do that next. Times the limit as x approaches 0 of sine of x. And then this will become 1/3 times this limit, which we know equals 1, times this limit, which I can use direct substitution for, sine of 0. So this will become 1/3 times 1 times, well, sine of 0 is 0, but that's okay. Like, we didn't get anything undefined, even though it will equal 0 in the end, which I know sometimes we feel cheated when that happens, but it's okay. 0 is a legit answer to a limit, so don't feel cheated, okay? So you guys, it's all about, rewriting that function and getting it to where we can use direct substitution. Really not a whole lot different than like factor and cancel or multiply by the conjugate. It's just here, because we're dealing with trig functions, in order to rewrite it, we've got to use our trig identities, and then we've got those two special limits that we can also use. All right, so you guys, we'll practice this in class tomorrow. Thank you for watching. Have a good night.